Hi, welcome to Why Physicists Are Good at Managing Uncertainties, Part 2. We said before that we wanted to cover a couple of things that physicists do that require managing uncertainty. We previously looked at the first of these, drawing conclusions from necessarily imperfect experimental data. In this video, we will look at the second of these, making simplified models of phenomena and knowing how good those models are. So the problem is this. We want to understand reality, represented here on the left by this cow. But reality is complicated. So to get a handle on reality, we build models, which have a lot of the complications taken out. Our model may be very rudimentary, as represented here on the right by this spherical cow. Or it might be somewhat more complicated, like this model of a cow that has at least legs and a head added on. No matter how much we try, our models will never include all of the tiny effects that exist in nature. But we can still use those laws and models if we can estimate how large the emitted effects are, or we otherwise know the emitted effects are small enough for what we want to do. All laws and models are approximations. So while it might seem important to ask, are our laws and models correct? It's actually better to ask, is the approximation we're using good enough? And we should note, good enough depends on what we're trying to do. We use models to make predictions about how reality will work. If we can estimate the sizes of the effects that our model leaves out, we can estimate how much our prediction will differ from reality. Then we can ask, will the difference between our prediction and reality be small enough for our purposes? If yes, we're good to go. Now, figuring out whether our model is good enough for our purposes may seem like a daunting task. After all, how do we estimate the importance of all the effects that we did not include? But in practice, we don't need to identify and study every aspect of nature that our model leaves out. If we're pretty sure that one effect or a few effects are much bigger than the others, we can just calculate the uncertainty arising from that effect or effects. And usually, this is good enough. Here, we're not going to go into detail about how to estimate model uncertainties. We're just going to give a few examples of activities that physicists have to do where they need to make and use models so that we can see what questions they have to ask and then answer. Okay, let's look at those examples. Okay, example 1. These days we know that Newtonian mechanics is not a set of absolute laws of nature. For example, we know that it is an approximation to special relativity, and at high speeds, close to the speed of light, the approximation fails terribly. But even though we know that it isn't exactly correct, we still use it. Why? Well, first, most people find Newtonian mechanics much easier to work with. And second, the predictions of Newtonian mechanics differ from those of special relativity by amounts that are suppressed by powers of v over c, where v is the typical speed in the scenario being studied and c is the speed of light. In everyday situations, v over c is really, really small. So for these situations, unless we need amazing accuracy and precision, the predictions of Newtonian mechanics will work just fine. So it's still a really useful model in everyday scenarios and in most practical applications. This ability to choose the paradigm to calculate in is very useful and something physicists have to do all the time. We want to choose a model that is both good enough for our purposes and easy to work with. but this only works if one has an idea of the uncertainties introduced by using the model. Okay, now on to example 2. Previously, we saw that physicists need to be able to compare error bars on measurements and predictions in order to test scientific hypotheses. But here's a question. Where do those error bars come from? For simplicity, let's stick to looking specifically at the error bars on experimental results. Experimental physicists have to identify and quantify sources of error that come into their measurement. They're never going to find all possible sources, but they must find the most important ones. This often means they have to model their own experimental process, and that includes modeling the physical process that they want to study and modeling their own experimental apparatus. For example, let's look at a particle physics collider experiment. We have two beams of particles, which we collide. These interact to produce new particles. This is the thing we want to study. We need to model the physics of that process. But we also need to model the beams of particles that we start with. For example, how well do we know the energies of the incoming particles? Then we detect the particles that are produced using a particle detector, represented here as a cylinder. We need to model the behavior of the detector apparatus too. Perfect models of the physics processes and the experimental methods are not possible. It is up to the experimentalists to reduce the sizes of these imperfections and calculate how they come into the final uncertainty on their reported results. This process may be quite involved, and the physicist may even take measurements of the behavior of their own measuring devices to update their model of their own equipment. Okay, and now example 3. Sometimes we build a model that we know isn't good enough for our purposes. So here we have a cow, representing reality, and a spherical cow, which is our not good enough model of a cow. Why would we build a model knowing it isn't good enough? Well, we want to understand reality, but our not good enough model with its simplifications is what we actually can understand. So we can study that not good enough model and understand its behavior. Then we can try to add in the most important pieces that the not good enough model has left out. So we can use that not good enough model to build a model that is good enough for what we need. Okay, let's review the take-home message from this video. The ability to build and use models of phenomena is something that physicists use all the time and has lots of applications. But it's very important to have a good idea of just how good your model is. So, it's important to ask, what are the most important effects that this model leaves out? And are those effects small enough for the purpose at hand?